Okay, next we are going to do an example. It's example number 22 on page 244. There's a runaway truck going 90 miles per hour, entering an emergency ramp, and the ramp is inclined at 15 degrees. We'll determine the length of safety ramp, so that L, shown on the figure, to stop the truck if friction is neglected. So given is runaway truck entering a safety ramp and length is L is being asked. And again, starting this exam, we are asking you to not worry about the layout and not waste your time to write them down, but definitely please think about them. So even though you're not writing, what is the assumption? What is the plan? How do I estimate it? Or at the end, does my answer make sense? Make sure to think about those, okay? You're just not required to write them anymore. Yeah, we are gonna, the assumptions are we are going to neglect the friction. And I usually add these two on my energy conservation, not in the assumption, but either way is fine. But in this case, since in the exam, for example, definitely write them somewhere to show, like, okay, if you're crossing delta I to 0, why, like explain why, okay, give some detailed solution. So that's what we are looking from now on in the exams. So I'm going to show the solution part, and hopefully you'll see what we are looking for you to show. And we are going to use the energy conservation and whatever else is needed. Could be work definitions and so forth. But we will analyze our plan again. Estimation, since there's no friction, this is not very realistic. You might have seen some runaway ramps. There are several of them in Pennsylvania. I've also come across. So they're not too long, but if you don't have friction, it's gonna take much longer. And if in the more order of magnitude, if I'm thinking about like 10 feet, 100 feet, 1,000 feet, 10,000 feet, I would probably say 1,000 feet because it's going to take longer to stop the truck. So we are like order of magnitude, I would probably say 1,000 feet to stop this truck because it's starting with like 90 miles per hour. Meanwhile, this is going to be the starting point, not on the other side. Okay, so this is going to be the initial point, and this is going to be where it stops by the end of the runaway truck is going to be the final point. So those are going to be important. So considering those 2 points, again, initially we are here, has a high speed, and we are going to set this point, again, as you can see here, upward to be y. You should always do that for potential, so you don't really have a choice on this. You have to say this is y, and you can choose where you want to put the 0. I usually put it at the bottom so that I don't have to deal with negative potential. And starting from there, so there's no gravitational potential. Initially it's 0, and at the end, this end, it's going to come to a stop. That means kinetic energy will be 0, but has some elevation, and that's the maximum elevation it will have. That means we have a high potential energy, gravitational potential energy. Now, first step is, again, you have nice figure. Let's just talk about the free body diagram. I usually do this after, like, as a kind of a second step when I work on my work term, but you can do it earlier as well. Since there's no friction, no drag, all those things are neglected. There's normal force upward and weight force. When I say upward, it is vertical to the surface, inclined surface, and there's weight force straight down, vertical to the horizontal. Those are the 2 forces. And again, the displacement is that way. So normal force and the displacements are perpendicular, but since weight force and the displacement are not perpendicular, there's some angle, and that angle here is 15 degrees. there will be work done by the weight force. And since the angle between D and W is larger than 90 degrees, we can also see that work is doing negative. The weight force is doing a negative work. But it's a question of, do we want to keep it as the work term or the potential energy? So we're going to discuss that. But again, we do not see the spring-like object, so there's no elastic potential energy for sure. Okay, so we're going to say this goes to 0, and this is the reason there's no spring. Okay, so we're starting kind of simplifying our equation. I'm gonna get rid of this first. Just want to say this is 0 because there's no spring. Okay, delta K stays there. Delta I also goes to 0. No, I'm gonna write it in this form. No T change, right? Or delta P. Remember what they are? T is for temperature, P is for pressure. Okay, there's no change on these, so that means there's no internal energy change. And delta UG is, again, there's a change in elevation, so we do have it. What do we want to keep it? And let's just say yes. Okay, and then that means I'm not going to use the work done by the weight force in this work term. Okay, so I'm going to talk about this soon. And heat is also 0 because there's no heat added or subtracted from the system. The good news is energy conservation, you can always use it. Okay, depending on what you need, you may not prefer using it, especially when they're asking for like time or something. You need to use maybe Newton's laws or constant acceleration stuff, but this is usually a way to solve problems now. So we end up with simplifying to this term, and we still need to work on the work term. Okay, so let's consider that now. So we need to look into our free body diagram again. There are only two forces, and the work force, so I usually write it this way. There is normal force work done, and there is the weight force work done. This is 0, and explain why, because theta is 90 degrees. Okay, and that's why it doesn't have that. And this term, although it's coming from my free body diagram, there's weight force. Although it's not 0, if they're asking me to find weight force, work done by weight force, it is non-zero. You need to write it down, okay? But when I put it in the energy conservation, I'm going to take it 0, and I'm going to say accounted as, it's not very nice writing. I'm going to give myself a little bit more room. It is accounted as delta UG. That's why you're taking it 0, okay? Okay, so it's keep pressing the wrong stuff. Okay, and so that means there's nothing left, right? This goes to 0 as well. So when you simplify it, then you will end up with just the kinetic energy and the gravitational potential energy changes, and when you add them up, it gives you 0. And now the next step is kind of writing what those deltas mean. It's final minus initial for each. So then you write this equation here. And now you're simplifying again, thinking about, do we have any 0 terms? Again, K final is going to be 0, and I also write some explanations on this. So this is 0 because V final is 0. It comes to a stop at the end. Initial is not 0 because it had that 90 miles per hour speed. We chose the initial, the bottom part, to be 0. Why? That is going to make the potential energy 0. So you're going to get rid of those and then rearrange your equation, and this is what you're going to get, right? We're putting the positive in the front and then negative Ki, and that means they are equal to each other. Okay, again, I'm not plugging any numbers there yet because it's gonna be harder to carry if you add numbers right away. So just try to, again, be patient, and you've been doing really good on that in the other problems, so you can do the same here. And let's write down what they mean. UG is mgy, k is 1/2 mv square, and we are writing the equation now. But we need to find, if you remember, we need to find the length L. It doesn't look like it's in my equation. The good news is we have a right triangle, and y final is opposite to the given angle, 15 degrees, and L is the hypo, so we can write this relation between them. So I'm really writing what sine theta is, opposite over hypo, and rearranging this for y final gives me L times sine theta, which is 15 degrees. So that's one thing, and from this equation you can also rearrange y final and kind of divide both sides by mg. M is gonna cancel out anyway, divide by g, so that's what you get right on the right side. And the geometry, you got this relation between y and L. To be able to solve for L, you are going to say that these two are the same thing. So first thing you do, L sine theta, or 15 now, equals to V initial square divided by 2g. Okay, and then you can leave L by itself. I'm gonna just show that. And then when you write L, this is what you get. Plug the numbers in now, right? And make sure units are followed. It's in English units. Miles per hour will go away here. And you have feet squared, second square, because you have square here. And divided by this, so one of the feet will go away, second squares will go away as well. Then you're just going to end up with feet as the unit, as it should be. So it's about 1,000 feet, and in terms of yards, it is a couple hundred yards, 349, and that's the answer. Okay, box this as well. So that's how you use energy conservation to figure this out. There is another way, and Newton's laws. And again, I'm not gonna really explain this much because we've done a lot of problems with this, but also look into this. You apply second law, draw your free body diagram carefully. Again, you have to have now careful coordinate systems because you are applying like which one is x, which one is y, right? You're applying second law now. For the work term, you don't need it because what matters is the displacement direction, and you're comparing the angles between the force and the displacement. But for Newton's laws, you have to have this coordinate system. And it can be different than what you chose before, and I would suggest just check. You don't have to use the same thing as before, as we assigned it for the energy conservation. So first thing you do is, again, get the acceleration. Once you have the acceleration, you have two motion equations. Since forces are constant, acceleration is also constant, so you can use these equations. And this is the condition, so you can use these equations. But energy conservation solves any problems, okay? You don't have to have constant acceleration. You can even solve problems without changing acceleration. That you cannot use these two equations here, but you can still use energy conservation. Okay, be careful with the conditions of the equations. Again, from this, you can also, you need to get the time first, and then you can solve for L, which is the same thing as before. But one other thing I want to highlight is energy will never give you what the time is. Okay, so if you need the time, you may need to use this form. Or maybe if they're giving you the power, if you remember, power is the rate of energy, so it's work done over time period. So then you may be able to get the time that way from the energy. And also, again, this L is quite large. It's because we don't have like friction. And if we didn't have friction and brakes as well, then the truck would just go like on the go back and down because it would come to a stop, but then has potential and then goes back down, transfers that to kinetic, and then stops again on the other side, and then kind of keeps rocking that way. Again, later on we will have friction as well, and you'll see more realistic problems.